the same as when you have these soluble compounds. Okay? So in Gen Chem 1, your solubility rules may be told you that these materials are either soluble or insoluble. But here in Gen Chem 2, the term that is insoluble in Gen Chem 1 is not really insoluble per se. At least it doesn't what we call dissolve in any way in water. It's just that their solubility is just so low. Okay, so to deal with the equilibrium, you must know the equilibrium constant. So we will look at the solubility of the slightly soluble or nearly insoluble ionic compounds, and show how you can determine them, what we call their solubility. So when an ionic compound is insoluble, as is stated in the solubility rule, or slightly soluble, you usually establish an equilibrium. Okay? So the equilibrium that you have there is similar to this one. So maybe you have M there, which is the metal component, and then X as the ion. And a very good example there will be AgCl. So when they dissociate, they can give you Ag plus and Cl minus. And if you're going to follow solubility rule, what will happen? If it's just in terms of the law of mass action, so maybe you can have it like this, right? But what will happen with this one, since this is what? Constant. You can incorporate it with K. So that K times this one will now become your Ksp. And that Ksp is just known as your solubility product constant. So you have another K here. Okay, so K is what we call solubility product constant. And the way you express Ksp expression is just like this one. So if you're going to express the silver chloride dissociation there, so Ksp is just equals to silver ion and chloride ion. So let's try to write the Ksp expression for the following reaction here. So whenever you have that, so you know that it's a solid, so they will dissociate to give you, what do you get here? Hg22 plus 2Cl minus, and both of them are aqueous. The same thing with this one, which is solid. When they dissociate, they have Hg22 plus 2Cl minus. So if you're going to put your Ksp there, so how are we going to do it for the first one? Anyone? So you just put there the so-called ion product. And for the B, you do the same thing. So that's how you do expression. So if ever you have what? A coefficient that is other than 1, you're going to use it to raise the ion product that you have there. So if it's just 1, it's understood to be raised to the 1. Question on this? Question? So if you're given a question like this in your exam, you can answer that. So let's try to solve number problem. So exactly 0.133 milligram of silver bromide will dissolve in 1 liter of water. So what is the value of the Ksp? So the way that we're going to do now is those Ksp, just like your what? Ka and Kb and Kw, they have their own value. Okay? So before I give you the value of the Ksp of what we call the different common salts, let's try to see how they determine this value. And the classic experiment that they have is they have 1 liter of water and then they add the materials and determine how much of the material dissolved. So how do you think they did this here? So maybe they have what? They have 1 liter of water and they had added what? Around 0.5 grams or around 500 milligrams. And then what happened? Only 0.133 milligrams of the silver bromide dissolved. The rest remain undissolved. So what they do, they might filter it and then the way that remains undissolved, they subtract it from the initial mass. So they found out, oh, this is the one that remains undissolved. And the difference is the mass that was dissolved. So this is just how they do this, what we call Ksp value. And from that, they were able to determine, okay, this is the amount that dissolved in 1 liter. So from this, we should be able to get the Ksp value. So how are we going to do this one? So the first thing that we're going to do, we're going to write the Ksp expression, which is just equals to what? Silver ion times bromide ion. Because if you're going to look at here, you have a silver bromide, which dissociates to give you silver ion and bromide ion. And then what happened? You can determine the equivalent in moles of the 0.133 milligram of silver bromide that dissolved in 1 liter so that you will get the unit in molarity. Okay, so for instance, if I have 0.133 milligram there, I can multiply it with what? For 1 gram, I have 1,000 milligram. Okay, and then for every 1 mole, I have the molar mass of my silver bromide, which I could give here as 187.77. So if you're going to have this, I can cancel this out. I can cancel this out, giving me the moles. And since I use 1 liter, I can get it as moles per liter. So what's the number that I have here? Hmm?
Sorry, I'm just confused where you got the 87.77 grams from.
What?
Where did you get the 87.7?
That's the molar mass of the silver bromide.
Okay.
So I would have here around 7.133 divided by 1,000 divided by 187.77. I have 7.083 times 10 to the
I don't know what I did wrong, but I got something completely different.
-7. Now, that represents the amount of the silver bromide that dissociate. And that is also the amount that you have here and also here. Right? Because there is a 1:1 mole ratio. So we could say at equilibrium, what do you have? You have those value. And then what you're going to do, you replace it in the Ksp expression. So Ksp is just equals to 7.083 times 10 to the -7 times 7.083 times 10 to the -7. So that is just equals to what? If you square those value, so you have 5 point. So you have 3 significant figures here times 10 to the -14. Oh, is it 14 or 13? Not 14. So that is your Ksp value. Now, what does the Ksp value tells us? Similar to your Ka and your Kb, the value in your Ksp conveys us some information. And just to show you, okay, these are just some of the value of Ksp value of some of the compounds. Now, what can you say about those values? They are always what? They're always a very small number. I think the highest number that I see here is this one. The rest are low, as far as this one, silver sulfide. Now the question is, what does those value means? Okay, I still have the value like this one. So those value means the lower the Ksp, or we could say the higher the Ksp, the more soluble the substance is. The lower the Ksp, the less soluble. But there's a big but. This is only true if you have the same type of salt. So what does it mean? You can compare the value, let's say, of silver bromide, silver chloride, okay, and silver iodide. And you can ask the question, which among the 3 salt is most soluble? Which among the 3 salt is the least soluble? So if this is the choices that you have, so I want you to answer. So which of the salt is the most soluble? Type your answer in terms of A, B, C. Right? Like what the Jackson said, A, B, C. Dun, 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 dun. 1, 2, 3. Dun, dun. Okay? So you can only compare the Ksp value if they have the same type. So what is the same type that I'm saying here? You have a salt that is +1 and -1. Okay, and if you ask you which is the most soluble, you go with the highest one. And which is the least soluble, you go with the lowest value. Is that clear? So, assuming that the salt that you compare are of the same type. So when I say the same type, what can I say here? Your silver has a charge of +1. Your anion has a charge of -1. So you can compare their Ksp. The higher Ksp value is more soluble. The lower Ksp value is more insoluble or less soluble. But you cannot compare, let's say, by just looking at the value between AgCl and silver chromate. Why? Because in this aspect, you have what? A -2 charge and 2 times +1 charge of your silver. So if you want to compare the solubility between the two, you have to determine its solubility. So solubility is in the form of what? Molar or just solubility, which is grams per liter. So molar is moles per liter. Okay? Later on, you will know how to get this if you want to compare the solubility between salt that doesn't have the same type of charges. Silver acetate, you can compare it with this one. What is your rule, solubility rules if you have acetate? Anyone? All acetates are soluble. So look at the value that they have. It's so high compared to the other one. And I try to look at the other one here. So you have here the mercury chloride. See that one? And then the lead chloride. So remember your experiment 15, my lab people? How did you separate the lead from the mercury and the silver? I think all of you got wrong answers on this one in your lab report. You always said, I think there, that the lead is what? Absent. When in fact, what happened? You separate the lead from the mercury and the silver by adding your mixture in a hot water. So what happened? Because of the Ksp value that's seen here, which is a little bit high compared to mercury, which is 10 to the -18, and your silver, which is 10 to the -10, your lead chloride will dissolve. So when it dissolves, that means it's there. Because some of you answer what? Lead is absent. Okay? But if you're going to look at the explanation there, lead is the most soluble among the among the insoluble, the so-called insoluble chlorides. Sorry for that. That's the hardest part living in Third Avenue. Okay, so let's try to get now the Ksp, but this time not the same as the one that we have before. The one that we have before, we have a +1 and a -1 charge, but this one you have a +2 and a -1 times 2. So it says here, an experimenter find that the solubility of barium is 1.1 gram in 1 liter of water at 25 degrees Celsius. So what is the Ksp at this temperature? So whenever you have a problem like that, you solve it first by writing the reaction. So BaF2, Ba2 plus 2F minus. And if you're going to write the Ksp of this, what are you going to have? Ksp is equals to Ba2 plus times F minus raised to the 2. Now, what are we going to do? We need to determine what's the molar solubility of this. So we have 1.1 gram. We multiply it with what? For every 1 mole, you need the molar mass of your barium fluoride, which I'm going to put here as 175.32 grams. And then you will have, what do you get? What's the answer? 1.1 divided by 175.32. So I get around 6.27 times 10 to the 3, -3 moles. And since I have what? 1 liter, I can just put that like that. Now, what does the reaction tells us? So if I have a BaF2 here, Ba2 plus 2F. So I can have what here? I don't have anything initially. You can still use the rise here. So what are the changes that you have? This is what? Plus X, and this one is, anyone? Why is it plus 2X?
Because they're coefficient of 2.
Okay, because of the coefficient of 2. So at what we call equilibrium, this is X, and then this is 2X. And what do? We're going to replace this expression here. So you end up with what? X times 2X squared. Analyze. Because my next question is, what is X?
So 6.27 times 10 to the -3rd.
So that's your X. So I'm going to replace the X there with that. And then I'm going to do it here. and then squared. And then that's what I got, the Ksp. So what's the Ksp? There's a lot of siren. So what's Ksp value? I don't know why there's a lot of siren at this time. So it will be 9 point. Analyze. Because you did the calculation that you're required to know in this chapter. You're given the solubility and you're going to get the Ksp. So you're given a condition wherein you have a +1 and a -1, and then you're given a condition where you have a +2 and a -1. So question, because the next thing that we're going to do is the reverse. When I say the reverse, you're given the Ksp and you're going to calculate for the solubility. So question, this is not included in the second exam, okay? You're already overloaded with calculations in the second exam. So the next one, as I've told you, it's the other way around. You're given the Ksp and you are asked for the solubility. Okay, solubility in terms of grams per liter, because if it's the molar, usually the term is molar solubility. So you have here mercury chloride, mercury 1 used as laxative. It has a Ksp equal to 1.3 times 10 to the -18. So you're asked what's the solubility of mercury chloride in grams per liter. So you're going to write still the expression like this one. And if you're going to write for the Ksp, it will be Ksp equals to Hg2 2 plus times Cl minus squared. So what are we going to do? We need to find the expression that we have here. So remember the initial changes and then the equilibrium. So if you're going to look at it, you're not going to deal with the solid. You're only going to deal with the ion product. So you have here what? Nothing. And then this one becomes plus x plus 2x. So this becomes x and then 2x. And then you're going to replace it here. And you're given the Ksp value, which is 1.3 times 10 to the negative 18. So you will have here x times, what is 2x squared? Four x squared times x will give you 4x cubed. And the way that you're going to solve is you're going to solve for your x. So how are you going to solve for your x? So I divide both sides by 4 and then get the cube root. So what's x? So what's the x? Anyone? So you will have 6.88, or as you could see, you only have what? Two significant figures. So you have there 6.9 times 10 to the negative 7. But that is in terms of moles per liter. So you're not yet done. Okay? Because the one that's being asked is grams per liter. So what are you going to do? So you have moles per liter. All you need to do is multiply it with grams per moles, which is your molar mass. Okay? So the molar mass of your mercury chloride would be around 472.086 grams per mole. So what is the amount as grams per liter? We got what? 3.3 times 10 to the negative 4 grams, or around 0.33 milligrams per liter. Everybody got that? So question, because as of now, you're able to get the Ksp if the solubility is given, and you're able to get the solubility if Ksp is given. Question. Question. Pregunta. Now, what if we have a common ion effect? So you were introduced on the common ion effect directly during your discussion or introduction of your buffer. But you were introduced to this indirectly when you add one of the products and how the equilibrium is shifted, favoring the reverse reaction. Now, the question that we have here is, what will be the effect of the presence of the common ion on the solubility? Will it become more soluble or less soluble, or there's no effect at all? Because as I have discussed before in equilibrium, which is your exam on Thursday, we can use the Chatterley's principle to predict that the reaction will shift in the reverse direction when M plus or X minus any of the common ion of your material is added, reducing the solubility. Okay? So let's try to do this one. What is the molar solubility of silver in chloride or silver chloride in 1 liter of solution that contains 2.0 times 10 to the negative 2 moles of HCl? Maybe before we solve this one, what if we just going to get the solubility of silver chloride? The normal one. So this is the reaction that you have. So if we have the normal one, what are the changes that we have here? Nothing in the initial, and this one becomes what? What do you have in your silver ion and chloride ion? So that's plus X, and this is plus X, and this is what? XX. So if you're going to look at this, this is just Ksp equals to silver ion times chloride ion. And your Ksp is given as 1.8 times 10 to the negative 10. So this one is X times X. So what is the X? Just the square root of 1.8 times 10 to the negative 10. So what's X here? What's the value that you get? What's the X here? Square root of 1.8 exponent 20 or 10. Negative 10. So that's 1.34 or 1.3 times 10 to the negative 5. And that is the concentration also of your silver ion, which is also the concentration of your silver chloride. Why? Because they have a 1:1 mole ratio. So that is in terms of molarity. I don't need to convert it to the grams. Now, what happened if we have this problem? What's the changes that will happen in the expression here? Anyone? What will happen if we have this problem? So what's the changes that we have here? So you have an HCl. So HCl will give you H plus and Cl minus. And that's what? 0.02. So you have here 0.02 and you have here 0.02. So that means this has 0.020 at the beginning. Did you get that? And then this is plus X. So what will happen? In the end, you will have 0.020 plus X. And if you're going to look at the expression here, this will become 1.8 times 10 to the negative 10 equals to X times 0.020 plus X. So what's the approximation that we can do here? We can simplify it to say that this is just equals to 0.020. The X value that you have there is so small. So the same concept that you have in weak acid and weak base. And if you have that, what will happen? So 1.8 times 10 to the negative 10. So this becomes 0.020x divided by 0.020. What is your X? So that's 9.0 times 10 to the 9, negative 9. Now I want you to compare the solubility without the common ion and the one with the common ion. And I want you to analyze how you get this, what we call thing. This number proves that the presence of the common ion chloride would, we could say, reduce the solubility. So from 1.3 times 10 to the negative 5, your solubility now is 9.0 times 10 to the negative 9. So there's a reduction of solubility by what factor? Okay, so it's really a big factor. It's not only reduced by twice, thrice. I think if I'm not mistaken, the solubility was reduced by a factor of about 1,400. So question, because I think I'm going to end my chapter 17 here. So question. Before I go to classes. So when you go to classes, so the answer key for the three chapters are here. And then you also have here the exam reviewer. So those are the questions. Okay. And then you also have the answer key. And in addition to that, I also have, if you read my email, in the lecture slide, I said there, all the links are available now. And then I put an additional slides there that has what? Chapter 16 problems.
Thank
So
you.
if you download that, you will what we call see the record that I have how to answer some of the questions.
I have a quick question.
I
have a quick question.
Okay.
Would you say that studying each chapter reviewer is smart for the test, or should we be studying like just the exam 2 reviewer?
Well, what is the rule that we have here in this course?
The more you do, the chem is try.
Yeah.
Okay, cool. I think that answers my question perfectly.
So when you download the PowerPoint, you will hear my voice there. Okay. So there are some problems there that I what we call included, like a typical weak acid problem, the percent dissociation, where when you have a dilute solution, it will ionize at a greater extent than a concentrated solution. So as shown here, if it's a 0.001, there's 0.062% dissociation. At 0.1, it's only 0.0062%. And then I have a weak base problem. And then I have a salt problem. What's the pH of salt? And then you have a buffer problem. Okay, another buffer problem. And then you have a titration problem. Okay, and you have a titration problem. So everything is already given there. And of course, you have your owl. So the question is 25 items. So question. If you follow what I asked you to do, I would say you're not going to have any problem. Okay. The things that I have both in the lecturer's lab is simple. Do it the way I told you to do. If you want it your way, then it's up to you. Okay. Your main enemy here is not me. When you point the finger with me, okay, I can assure you 3 of your fingers is pointing it to yourself. So that's your main what we call enemy. So question. Hello? I have my voice. No, I have my voice. No, I think the reference sheet is oh, shit. Where's exam two? I'm going to email you the reference one. So you should get the email now for the reference. Yep, I just email you the reference that you have. We don't have any exam dry run because I'm just so loaded at this time. I cannot do anything anymore. Okay. So the one that you have here, 31. Yeah, I wasn't able to do the dry run because most of you asked for how to answer Lab 18. So I have to do the weekend doing that, what we call presentation thing. So I think it's about time that you need to learn to be independent because when you go to what we call organic chemistry, you're going to have some sort of a culture shock. Because my way of saying to my students that you'll never be alone here in Gen Chem, on your organic chem, you're on your own. So chapter 16. Number 31. Is this the one, Annie? So if you're going to solve problem like this, so you have here the volume and the molarity of your acid, so you can get there the moles of your acid. Now you have here a base. So what does the base do? When you add the base, the acid will be converted to its conjugate base. So whatever the moles of your conjugate of your base that you added, that's the number of moles of your conjugate base that form. Okay, and you have there the 2.910, and you need to get the Ka of HF, because the way that you're going to solve this problem is you just use what we call Henderson-Hasselbalch. So you have the pH equals to pKa plus log of base over acid. So you're given this, you have to get this, you're given the number of moles for this, so you're going to calculate for that. Because they may have the same moles here, and they're what? In the same volume, so the volume will just be canceled out. So that's how you're going to solve the problem then. So you're going to rearrange it in such a way. You have here what? 2.910. And then you have to get the negative log of the Ka of the HF. Okay, and then you have, you don't know, the log of the base. But you can get the moles of your acid, which is the volume times the moles per liter. So the volume should be in liter. So to give you the number of moles. So once you have that, you should be able to calculate for the base. So question there. That's how you're going to do it. So if you're going to plug the math there, so what do you have here? 0.225 liters times 0.465 moles per liter. And then you need to find the Ka of HF. So what is Ka of HF? Around 6.6 times 10 to the negative 4. So if you're going to get there the number, so that will be what? Negative log 6.6 exponent negative 4. So you have here 3.180. So if you're going to do it here, what will happen? So how do you remove the log? Can it be like this? So if you have that, you might get around what, 0.1? and then you multiply it with your 0.105. So most likely the concentration of your base is around what? 0.0107, the number of moles. Then you can double check that to what we call make sure if it's the right one. So you're going to plot this number here, this number, which that, whatever number that you get here, which is 0.105, and then see if you're going to get a 2.910 if you add that thing there. Or did I make a mistake somewhere here? I might make some mistakes here. 2.910 minus 3.180. Oh, I think this is the one that I made a mistake. So instead of 0.99, that's 0.27. So this is a negative 0.27. So that number is not the right one. I think you will have a 0.53 here, 537 times 0.105. So the number that I get is 0.0564. Okay?
Professor, I have a stupid question regarding the pH. Like when it equals 14, it's only at 25 Celsius
Yeah.
and it's going to be like said in the equation.
No, I mean, the value that you have for Kw, the 1 times 10 to the negative 14, just only for a certain temperature. If you're going to change the temperature, that value will change.
Okay. Thank you. It makes sense.
So you're going to use also here your what we call Henderson-Hasselbalch equation. So you get the pH, which is 7.490, and then you get the negative log of the Ka of your hypochlorous acid, and then you determine, okay, the ratio that you have here. So if you're going to look at it, you have the weak acid and then you add a hydroxide, you're going to produce the conjugate base and H2O. So the way that you're going to look at this, you determine the moles of your acid. So 0.336 times 0.150 liters. So that means, okay, you have this value here of your hydroxide, which is what, 0.396. So you need to get the corresponding volume there. So usually what happens, okay? So whatever the volume that you have here, that is the amount, or whatever the moles that you have here, that's the moles of your hydroxide that form. I mean the conjugate base that form. So this is what we call 7.490 here. And you should be able to get the pKa of the hypochlorous acid. So if it's hypochlorous acid, that is what? I think that's the HClO thing. And that's 2.8 times 10 to the negative 8. So that will be equals to what? Negative log 2.8 negative 8. So that's around 7.55. So you have to vary what would be the value of the base so that when you add it to this one, it will give you this pH. The same thing as we did earlier. No, usually it should be given to you, or you should have to get it. In the exam, it will be given to you. Unless that's the one that you are asked to solve. All I can assure you, I think, is the OWL is a little bit more challenging than the exam. But it doesn't mean that you have to be confident or you're just going to procrastinate. Because I already what we call learn my lesson, not to tell my students that the exam is easy. Because when I ever tell my students that the exam is easy, what happened is they're not going to study. But they have to, you have to understand the concept of me is easy is very different with the concept of you that's not what we call easy. I don't know how many math questions will come out, but there would be a lot, we could say more than the one that we have before. Question. Now, I want your responders lockdown to be like me right now. Okay? Because usually if it's like this, you're going to get a red flag. So as much as possible, I don't want any red flag in the second exam. So how do you avoid the red flag? Make sure your whole head is within the screen. So you have a calculation in equilibrium. You have a calculation to get the hydronium ion and the hydroxide ion, the pH and the POH. Okay. You have a Ka calculation. You have a buffer calculation, and you have a titration calculation. I think that's the thing that you're going to have. Yes, DS have 25 questions. So we'll just need to, we're just going to meet 2 to 3 tomorrow. Because my, what we call schedule, is becoming busy until the end of March. That's why I'm hoping that those answer key could help you. If not, you can always go to the what we call office hour. And I want everyone to ask, not only letting one student to ask all the questions. So I would suggest go over all the reviewer, try to answer them as much as possible without looking at the solution. And then after that, you start looking at the solution. Why is the answer like that? So question. And I want you to, what do I have to tell you? Anyway, I'm just going to email that to you if ever, because we're still not sure if it's going to push through or not. So question. Question? Still have 5 minutes. Now, for those who are in my lab, I'm not going to send any more thing for chapter 19. Okay? The lab information is enough to tell you what to do. And if it's not given there, you just need to use the formula that is given in your protocol. Now, for those who have problem with their lab instructor, please update me on what happened. Because I already talked to the other lecturer, and I also emailed the instructor and all the lab instructors some strong worded statements. And I never heard anything from the instructor. Because I think it's going to be unfair for the other one. What will happen? Best case scenario, all of you will get 100.